We've seen that a number of addition reactions to alkenes proceed through three-membered rings, either as an intermediate or as a final product in the case of the MCP-BA oxidation. There's another addition reaction to alkenes that proceeds through three-membered rings that involves species called carbenes. It is actually a synthesis of cyclopropanes. So we're making a carbon-carbon-carbon three-membered ring instead of a carbon-oxygen-carbon three-membered ring like we have in the epoxides. So the reaction is quite simple. If we start with trans-3-hexene, and we treat this reaction with chloroform, in the presence of base, chloroform and KOH, what we'll end up with is a cyclopropane ring where there are two chlorines attached to one of the carbons. The combination of KOH and chloroform creates an odd species called dichlorocarbene, where we have simultaneously a lone pair on carbon and an unfilled orbital on carbon. So we have an empty p orbital that can act as an electrophile to accept a pair of electrons from the pi bond, but we also have a sp3 hybrid, an sp2 hybridized orbital with a pair of electrons in it. Right, a filled sp2 hybrid orbital and an empty p orbital. So we have a molecule that is both nucleophilic and electrophilic at the same time. Nucleophilic because of the lone pair, and electrophilic because of the empty orbital. But there's no formal charge, right? It's a neutral species because carbon brought 4 electrons with it from its valence, and it still has 4, the 2 lone pair electrons and half of the bonding pair electrons, 1 each from each of the 2 carbon-chlorine bonds. So, 2 questions. Where does the dichlorocarbene come from? How is that generated from potassium hydroxide and chloroform? And once it is generated, what's the mechanism of reaction to dichlorocarbene with the pi bond? And you'll notice that it was a stereospecific reaction. The 2 ethyl groups are trans to each other in the starting material, and they're trans to each other in the product. So, interesting thing about chloroform is because of the 3 electron withdrawing chlorines, the hydrogen on chloroform is significantly more acidic than an ordinary carbon-hydrogen bond would be attached to an sp3 hybrid carbon. Ordinarily, an sp hydrogen would have a pK of 50. This is much more acidic, which means that potassium hydroxide is a good enough base to remove it. The equilibrium constant lies way to the left because it's still significantly less acidic than water. But it's acidic enough that it can happen. To generate a carbon anion, But it's a carbon anion with 3 good leaving groups attached to it, right? 3 chlorine atoms that are attached to it. So what we see here is an alpha elimination. Normally, we only see beta eliminations, right? When we did the E2 and the E1 elimination, we're always removing a hydrogen from the beta position relative to the leaving group. But in this case, there is no beta position. Right? There is only the 1 carbon. And so we're losing the chloride ion and removing the proton from the same carbon in a 2-step process to generate chloride and the dichlorocarbene, which has a lone pair on it that used to be the negative charge, and 2 chlorines. Once we have the dichlorocarbene, the mechanism is concerted, which is why it's stereospecific. We have the pi bond of the alkene attacking the MTP orbital on carbon, and that generating a partial positive charge on the carbon, into which the lone pair and the sp2 hybrid orbital donates. Generally, when we're working with a concerted reaction, it's customary to draw the transition state. And so we would draw the transition state for this. Showing that the pi bond is partially broken. We're forming a sigma bond to the carbon and another sigma bond to the same carbon, and we have our 2 chlorines attached. So we're forming 2 new carbon-carbon sigma bonds and breaking a carbon-carbon pi bond. The pi bond is relatively weak, that's only 65 kilocalories per mole. And we know that the carbon-carbon bonds in cyclopropane are also roughly 65 kilocalories per mole, but we're forming 2 of them. Which means that this reaction is energetically downhill, even though there's a strained ring, because we're forming 2 bonds that are approximately 65 kilocalories per mole and breaking only 1 bond that's effectively or approximately 65 kilocalories per mole. So this is one way to generate a carbene, is by treating chloroform with strong base, and that generates dichlorocarbene. And that's great if what you want is a cyclopropane ring that has 2 chlorines attached to a carbon. But that's not always what you want. What about making a plain old cyclohexane, or cyclopropane, that just inserts a CH2 group into the carbon-carbon double bond instead of a CCl2 group? Can we make a methylene carbene? And the answer is yes. We can make methylene carbene. It's very unstable, as are all carbenes, because they have an unfilled octet on carbon. But we can make methylene carbene in one of 2 different ways. One of which actually generates methylene carbene, and the other of which generates something which we call a carbenoid. Which is a group that acts like a carbene, but is not actually a free carbene. So we can generate a carbenoid by a reaction called the Simmons-Smith reaction that treats diiodomethane with a zinc-copper couple. Right, there's an electrochemical difference between zinc and copper, and effectively inserts a zinc in between one of the carbon-iodine bonds. So what we get is a carbenoid species where we've got the zinc bound to one of the iodines and the CH2. This molecule will react with a pi bond to insert the CH2 group into the CC bond in a concerted fashion to generate the cyclopropane, and zinc iodide as the other product. So it's not a carbene, but it acts like a carbene. This metal complex here and it's considerably safer than the other method of generating methylene carbene, which is from diazomethane. Because diazomethane is a low boiling low boiling liquid that is highly toxic. And explosive. What could be better than something that combines danger from explosion and danger from poisoning at the same time? Methylene carbene is generated in 2 steps. The starting material is a compound called N-nitroso, N-methylurea, and treating N-nitroso N-methylurea with base, usually in diethyl ether as an inert solvent, will result in diazomethane which has the structure shown. The mechanism for how N-nitroso N-methylurea reacts with base to generate diazomethane will be covered in the second semester course in chapter 21 on amines. It's quite complicated. It involves nucleophilic acyl substitution reaction at the carbonyl group to break this nitrogen-carbon bond, and in a series of proton transfer steps, this oxygen is lost as water, and the other products are K2CO3 and ammonia. But the reagent we care about is the diazomethane. Diazomethane, when heated, or activated by light, or a copper catalyst, spontaneously loses nitrogen gas and generates the methylene carbene. And if we want to see how that occurs, we can apply great rule of organic chemistry number 1, which is when you want to know how things react, you should look at the minor resonance structure. This is the most stable resonance structure for diazomethane. It's the resonance structure that has Philbot text and puts a negative charge on the most electronegative element. But there's another resonance structure for diazomethane that could be generated by moving this pair of electrons from the negative charge to form an N-N triple bond and puts the negative formal charge on carbon instead. Right, less stable because the negative charge is on the less electronegative carbon rather than the more electronegative nitrogen, but still a legitimate resonance structure. All nitrogen has to do is leave with this pair of electrons to form the very stable nitrogen gas and generate the methylene carbene, which is both electron deficient because of the unfilled p orbital and electron rich because of the pair of electrons in the sp2 hybrid orbital. And methylene carbene will insert into a carbon-carbon pi bond using exactly the same concerted mechanism as the dichlorocarbene that we saw from treatment of chloroform with sodium hydroxide or potassium hydroxide. That one was an alpha elimination. This one is just a light or heat-initiated decomposition with the loss of nitrogen, and that explains the explosive nature, because the nitrogen gas is liberated, and in the presence of a lot of heat, this exothermic reaction as well, that nitric gas can expand and cause problems. Diazomethane has to be generated and used in special glassware where you have polished ground glass joints so you don't have any abrasive or rough surfaces. If you use a ground glass joint, that also can generate nitrogen. So it's important that you not scrub your glassware with a wire brush and scratch the surface. There was an incident when I was at the University of Utah where someone decided that it would be a good idea to rotovac their solution of diazomethane in ether and basically vaporize most of the rotovac because of the explosive decomposition. It was a bad idea anyway because diazomethane is more volatile than ether, which means you would have rotovac'd away the diazomethane and left the ether behind. So that student wasn't very popular with his research advisor after that incident. Right? So we can generate methylene carbene by treating N-nitroso N-methyleneurea with KOH in the presence of ether to generate diazomethane, and then with heat or light under controlled conditions or a little copper catalyst, we can cause the controlled liberation of nitrogen gas and formation of methylene carbene, which inserts into a CC pi bond, or we can use zinc iodide or zinc copper couple and diiodomethane to generate the carbenoid through the Simmons-Smith reaction. Both of those reactions will generate a cyclopropane ring, and because they are concerted mechanisms, they will generate a three-membered ring with retention of configuration of whatever else is attached.